12.
12?
Yeah.
12?
Yeah. Yeah, it's a small class. Hello. Okay, so let me remind you what we did yesterday, like what we learned. Oh, you don't have a packet, or do you? No. All right, so yesterday we started this unit on something called differential equations, which is just basically, all you need to know about it is like it's an equation where the derivative appears as like a variable. And so the point of differential equations is you're finding what is the function that will satisfy this equation, like with the derivative and everything. Okay. So yesterday we mostly, like we haven't learned to solve these yet. All we've learned to do is like, well, we solved one very basic one. But all we've learned to do so far basically is verify that something is a solution. Like here's an equation, show that it is indeed a solution to this differential equation. Today we won't be solving them either, but we'll be learning a new way, like basically how to graph differential, or yeah, how to graph differential equations. And that is through slope fields. Those slope fields, what these guys are, is, well, let me just read you this, because this was put very well. So bear with me as I read a lot of words. It says, solving a differential equation analytically, like with algebra and stuff, can be difficult or even impossible. However, there is a graphical approach you can use to learn a lot about the solution of a differential equation, which can give a nice visual of the solution curves. Okay, the way you graph it is called slope field. A slope field is a graphical representation of the general solution to a differential equation. A particular solution in the slope field is this continuous function passing through some initial point that you're given. Okay, so how do these work? Basically, you'll graph a bunch of little slopes, little slices of lines that will together make up some sort of shape, some sort of a curve that would like in theory, it should show you exactly what the original function looks like. So let me read you some more. Recall that a derivative function gives us slopes of a function at a point. When we work with differential equations, we're dealing with expressions in which the derivative appears as a variable. For example, we might be asked to analyze the differential equation dy dx equals x squared. Okay, so remember this dy dx just means this is the slope at any point. So if we replace the dy dx in the above equation with what it represents, then we get the following statement: the slope at any point is equal to x squared. Hello. What is this? Oh, thank you. Do I keep the whole folder?
Yeah, you can, because I don't want to look into the junk description. But anyways, let me take the short test for 2 weeks ago.
Let me see if I have. Yeah. All right, good luck. No, give it a school.
Okay, bye.
Okay, so again, sorry. If we replace the dy dx with what it represents, then we get that the slope for this function at any point is equal to x squared, the x value squared. All right, it's possible to learn a great deal about a differential equation even when we don't know how, or pretend we don't know how to, because we could solve this. We do know whose derivative is equal to x squared. But if you pretend you don't, then what we can do is graph one of these slope fields and look at the picture that it makes. Okay. This I don't need to tell you. This I kind of already told you. I'm not going to read that. Okay, and this you'll see this is like embedded in an example. So let's just get to an example. I can feel you guys are falling asleep, so let's do an example. Okay, so here's what a slope field looks like. If you tuned out, here's the time to tune back in. So it looks like we're given a slope field for this differential equation. This is what slope fields look like. Again, this tells me this is the equation for the slope at any point. So they just took a bunch of points, plugged them in through here, and found out what the slope should be. And then they made little slices of lines with those slopes. And so you can see that it kind of gives us an idea of what the original function would look like. There's nothing to do here, but I'm just showing you how to read these. For example, if I want to see the solution through the point 0,2, then what you do is you go to the point 0,2, which is like, I'm guessing right here, because I'm seeing it. You go here, and then you just follow the lines and see what sort of shape it makes. So it looks like I start off flat, then I start getting steeper, 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 and then I get really steep over here. And to the left, I go like this. I start getting steeper in the downward direction, and it looks like this. Okay, so this black solution would be me using the slope field to find the particular solution that goes through 0,2. That's how they got this line right here. Okay, and then similarly for all these other ones, let's do like a couple more. Like in pink, I'll do this 0, -1. 0, -1 is right here. Okay, is that right? Maybe this one? I don't know, whatever, I'll say it's this one. Okay, 0, -1, if I follow this little line, it looks like I'm flat, flat, flat. I go up, and I get steeper, then flat, flat, go down, get steeper. Okay, that's how they got this one right here. All right, through 0, 0, this will be the last one. This is how you read these. All I'm showing you is how you read these. At 0, 0, if I follow these little lines, it looks like I'm going down at this angle, then I get flatter, flatter, and then start going up. And same thing over here. Get flatter, flatter, and then start going down. So something like this. And that's how they got this one. Okay, so that's how you read slope field. And again, what this tells you is like, this is what the solutions to this differential equation look like. Another way to think about it, here is the derivative of a function. These black, purple, and pink lines tell me what the original function might look like, depending on where I'm starting. Okay, so hopefully this is making sense. If not, we have a lot more examples. So hold on to your questions for right now. Okay, here's the first thing where we have to do something. So it says draw the slope field for this. All right, the way slope fields work is like this. You just pick a bunch of points, get what this, like plug in the correct numbers, and then you'll get what the slope is. So for example, just choose a point. I think the most natural one would be the origin. So if I take the origin and I plug it in through here, it looks like my x coordinate is 0, so my slope will be 0 squared. It's my x coordinate. So 0 squared is obviously 0. Okay, so that tells me that the slope for my original function at this point was 0. Meaning I'm going to make a slice of a line with a slope of 0. A little tiny slice with a slope of 0, so flat. Okay. Then if I just take any other point, like for example 0, 1, this point right above it, then my x coordinate still is 0, so 0 squared would be my slope. So my slope at 0, 1 is also 0. So a flat line. And in fact, anywhere along this line, since this does not depend on the y value, it only depends on the x value, all of these are going to be flat. See what I mean? No matter what I plug into here, all my x coordinates are 0 anyway. So all of these will have a little slope of 0, 0, 0. All right, okay. Next one would be like, I don't know, let's see what the slope is over here. Okay, if I take 1, 0, and I plug it in through here, my x coordinate is 1, I meant. So my slope would be 1 squared. Okay, 1 squared is obviously 1. And so at this point, my original function has a slope of 1. So you kind of have to estimate, but like this looks like a slope of 1. It would be going through these corners. The little slice of that line would look something like this. And then, like I said, my differential equation doesn't depend on y at all. No matter where I am on this line, like at the y coordinate 1 or 2 or whatever, they'll all have the same slope. Does that make sense what I'm saying? This does not have a y in it. Okay, I'm getting a lot of blank looks, so let me just show you what I mean. If I plug in 1, 1 instead, my x coordinate is still 1. My y coordinate does not affect the slope at all. So 1 squared is equal to 1. So still at 1, 1, I still have a slope of 1. And then if I plug in 1, 2, my x coordinate is still 1. So 1 squared is still 1, so it's still a slope of 1. The same is true for -1 and -2. These will all have a slope of 1. These look like I kind of changed the slope, but they're all supposed to be the same steepness. All right, and then let's do a couple more. At 2, 0, my x-coordinate is 2, so 2 squared, because of this, is 4. Therefore, at 2, 0, I have a slope of 4 in my original function. Meaning I'm going to make a slice of a line with a slope of 4. So a pretty steep line, something like this. Like 4 times as steep as this. Steep line here, for the same reason as the other ones. Steep line here, steep line here. Okay, hopefully, are these kind of making sense? You see what I'm doing? All right, good. Cool. Then let me go fast through these other ones. At all of these points, my f-coordinate is -1. -1 squared is 1, so little slice of a line with a slope of 1, slope of 1, slope of 1, slope of 1, slope of 1. All right, and then same thing at -2. -2 squared is 4, so a slope of 4 would be pretty steep. Okay, nice. And then you're looking at that and you're like, oh, okay, nice, so that's a bunch of lines. So what does that tell me? Well, remember what this tells you. This tells you what the original function would look like who has a derivative of x squared. And okay, so we know how to solve that. So now just use your intuition for what we know. We know that if something had a derivative of x squared, the original function had to be some sort of cubic function, x cubed, or like 1/3 x cubed, but whatever, something x cubed. Okay, so how does this show up here? Well, look at this. Just choose one point to start at. I'll choose, like, I don't know, 1, 0. If I just start there and I follow along with this slope field, I should, if I did this correctly, get out a cubic function. And let's see if that's true. So here I should start off pretty flat, then get steeper, and then really steep. Here I should start off pretty flat and get steeper this way, and then pretty steep. And indeed, you see, I get like a little cubic function. You don't have to write this if you don't want. I'm just trying to show you how this relates to the thing. What's up?
So when you draw the line, you are going to start from 0. Wait. Like if you did one of the ones that like has a slope of 4 on the left.
Yeah. Okay, that's a good point.
Then you would like go way too high, right?
Yeah, that's a good point. So like if you wanted. Like if it asked you to start over here, you should still get the same type of thing. So I start off pretty steep, then as I go left, I get flatter, and then I'm completely flat here, and then I go like this.
So if you start from the left, like that one, would you go when you have to go up 4 or no? I guess.
Oh, not really. More like I'm trying to copy the steepness here, but then I'm reading the whole thing. So I'm pretty steep here, but then I'm getting flatter. I mean, it is an estimation. Like you won't get the exact answer, but you should get the same type of graph no matter where you start.
Yeah.
Cool. Okay. Actually, the next question is about that. The next question says sketch a solution passing through the point 0 with -1. So that's exactly what we just did. Okay. So again, the way these work is you'll go to the point 0, -1. Let me do it in a color. What color do we like? Rainbow? So if you go to the point 0, -1, here it is, 0, -1 right here. Okay, you start there, and then you follow the lines, and you see, like, you estimate what the original will look like. So following the lines, it looks like pretty flat, pretty flat, pretty far, flat, start getting steep, start getting steep, start getting steep, and then flat, 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 steeper, 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 and then pretty steep. That looks like that. I have a rainbow on it. What is that rainbow? Not visible. Okay. You see rainbows?
Oh yeah.
Oh yeah, okay. All right. Okay, so that is like drawing and using slope fields. Now this is the type of question that you might see on an AP test where it's like, which one of these is the solution to the slope field? In this case, we're asked to match the differential equation to its slope field. So for this one, you need to use some tricks. So for example, this first one, if I'm trying to find its slope field, then I gotta like find a way to differentiate this one from all the other ones. So what I see as special here is that this is the kind of trick that you guys will get used to finding. This one has no y value, like this does not depend on y, it only has x's. So you don't have to write this, but just so I can refer back to this, this one does not depend on y. And so the reason that's special is because of what would look like, just like the one we just did, since this differential equation does not depend on y, then no matter where I am on a vertical line, all of those slopes should be the same. Like if I look at the point 1, 0 or the point 1, 16, all of those should be the same because the y value doesn't affect the slope. So again, I look at anywhere along this line, all of these slopes should be the same because this does not depend on y. So the point 0, 1, the point 1, 0 or the point 1, 1 or the point 125 or the point 1, 100 should all have the same little slope. Okay, so do you guys see any where the slopes are the same vertically? You see what I'm saying or no?
B.
Okay, thank you. Yeah, B, this one would have to be B because all of these slopes going vertically are the same. They're all the same steepness. And again, that's because this does not depend on y. So this one has to be B. Okay, so B is taken care of. Okay, then this next one, I mean, you can use the same trick, but now this one doesn't depend on x. So the slope should be the same in what direction? Like this, along the diagonal. Yeah, okay, good. Along a horizontal direction, the slope should not change. So which one is that? Say D is in dog? That looks correct to me because as long as I go like this, I see no change along these slopes. So this one is D is in dog. All right, then for the next one, you have to use a new type of trick. So what's a good color? Blue, green, green. Okay, for this next one, it depends on both x and y. So what might be something special about this? Can you guys think of any tricks that makes that special? Something easy to look for as x and y change or something about it? Yeah?
Well, I mean, if you like combine the last two, it means like all the slopes are different.
Okay, right. All the slopes have to be different because like both the x and the y are changing. However, both of these, all the slopes are different. But that is a good place to start. You guys see anything else that might differentiate it? You guys are brand new to this, so I don't expect you to like know some stuff. But somebody in my last class did say something pretty helpful. Yeah. Yeah, that's what somebody else said, and that's something that I had not thought of. I'll tell you what I thought of in a second, but that is really, really helpful. Notice that this one is negative. So that'll help you because that means that if x and y are both positive, then I should get a negative slope. If x and y are both positive, then this fraction is positive, meaning that the negative will make it negative. So what I'm saying is anything in like the first quadrant, both x and y are positive, so this would be positive like 6 over positive 7, and then making it negative would make it a negative slope. So anything in the first quadrant here, but you don't have to write this, just so you know what I'm pointing at. This negative means that anything in the first quadrant, says both the x and the y would be positive, would turn out to be a negative slope. Okay, cool. So here's my first quadrant. All of these are negative slopes. Is that true over here? No, all of these are positive slopes. This one has to be C. Okay. The other thing that I was going to say, like the thing I thought of when I was making my key, is that this is a fraction. This one is more complicated, so I would not recommend this. But just in case it ever becomes relevant, this is a fraction, meaning like as my y coordinates change, my slopes should be getting less and less flat. So like for example, if I look at the point 1, 1, then I look at the point 1, 2, then I look at the point 1, 3, these should be getting flatter because that would be getting negative 1 over 1, plugging them into here, negative 1 over 2, negative 1 over 3. So as I go up the y-axis, they should be getting flatter and flatter. And that does seem to be the case over here. Flatter and flatter and flatter. One more trick, I know you guys are bored, let me just say one more trick. One more trick would be to say, oh, well, look at this, this is a fraction. So if I look everywhere where x is 0, in other words, if I look at the y-axis, that's where x is 0, all of those slopes should be flat. It would be 0 over anything. 0 over anything will just be 0. So along the y-axis, all my slopes should be flat. So that is true at C as well. So these are the kind of tricks you can think of yourself. Any of them work? I think this negative one is really clever, and I did not think of that beforehand. So good job. Okay, so this one should be C, meaning that the last one has to be D, or sorry, it has to be A. Because we're out of choices. But if you go home and think about why this one has to be A, if you think about some tricks, then that would be good for your education. But it's Wednesday, it's a short day, so let's move on. And then what does this spell, guys? BDCA. Yeah, good. Isn't that kind of fun? Says the big guy. Okay. Okay, this last one has 3 parts to it. All of them are fine, not that hard. It just says, first, make a slope field for this differential equation. Okay, so let's make a slope field. We're going to have to plug in a bunch of stuff, but that's okay. So just choose a point. The natural one would be maybe 0, 0. So if I start at 0, 0 and plug that into here, it looks like I only need x values. So that would be 2 times 0, because that's my x-coordinate, over 0 squared plus 1. That's equal to 0 over 1, which is 0. So at 0, 0, I should have a flat slope. And then also, let me use that same trick from before. Notice this has no y's in it. So the y-coordinate isn't going to change it. So anything along this axis is going to have a flat slope. Okay. You guys good when I say there's no y's in that, so it won't affect it? Okay, all right, good. Cool, all right, then let's find out the next one. At 1, 0. That would be 2 over 2, which is 1. So at 1, 0, it looks like I have a slope of 1. And anywhere along here, I'll have a slope of 1. So just kind of estimate what a slope of 1 would look like and draw a little slice of that line. Okay, nice, nice, nice. Then maybe 2, 0. My x-coordinate is 2, so plugging that in would be 2 times 2 over 2 squared is 4 plus 1. That's 4 over 5. So a little bit less steep, because this is smaller than 1. Okay, so let me see how I can do that. That's a little bit less steep, just barely less steep. Okay. And then let's check what's going on the other side. Negative 1, 0 would be negative 2 over 2, which would be negative 1. Okay, so this one has a slope of negative 1. That would be something like this. Draw a little slice of that, little slice of that, little slice of that. Okay. And then if I plugged in the negative 2, you'd see I get negative 4/5. So let me do something similar. A little bit less steep, a little bit less steep. Okay. That one's pretty flat, but they're all supposed to be the same along the slope. Cool. All right, so we sketched the slope field. Now it says to sketch a solution along the curve that passes through 0, 1. Meaning like start at 0, 1 and follow the little line. So here is 0, 1. Before I influence you, see if you can get the same curve that I'm going to get. So try that. See if you get the right thing. Draw it maybe lightly if you're not super confident, so you can erase it. Okay. See if you get the same thing. If you're not done, don't look up yet. But it looks, your thing should look like pretty flat, getting steep, getting flatter. Pretty flat, getting steep, getting flatter. Were you close? Yay, okay. Okay. Then the next thing, last thing, is to find a particular solution for the differential equation. Remember, all this means is find the function whose derivative is this that passes through the point 0, 1. So should I write that? I don't know. I'll write it. Whose derivative is the one given. This is a terrible way to word it. Really, I should have said what function has this derivative and pass it through 0, 1, but now I've committed to this. Whose derivative is the one given and passes through 0, 1. This is basically what we were doing yesterday. So in other words, find the original function. So we got the derivative. We need to find the original. And find the c value. I think you're good.
Interrupt the shot.
Yeah, you're gonna ruin my shot.
Clean takes. Am I affecting the lighting?
No, it still looks sweet.
I would use some, yeah.
Oh, thank
Told
you.
them that was 5% extra credit. I think I used the wrong one, but
Hey, all right.
that's why you did a good job. You got this.
All right, so let's do that last bit. I know that, okay, dy dx is equal to 2x over x squared plus 1. Okay, so if my derivative is this, how am I going to find the original? What operation or whatever do I do? Got the derivative, need the original. Okay, all right, thank you. Yeah. Anti-differentiator, or integral. Okay, so let's do the integral of this function. Okay, and we have 6 minutes. Oh, I thought it was 2:35, but we have 6 minutes. So I would let you guys try this if we had more time. Will you at least tell me, do you guys know how I might go around about doing this? Yay, okay, good job. U substitution with U being what? Nice. That way my du is exactly 2x dx, which is exactly my leftovers. So therefore this will turn into 1 over u du. Meaning that my antiderivative is natural log of absolute value of u plus c. Did I lose you?
No, I just did.
Oh, okay. And then natural log of u would be natural log of, watch this, this is kind of neat. This is absolute values, but since x squared plus 1 is always positive, like you can think about that, then I don't really need the absolute values, which I think looks cleaner. So if you kept the absolute values, okay, it doesn't matter, but I just think this looks cleaner. And then, okay, so there's my antiderivative, but I got to find the c value as well. Do you guys remember how to do that? Okay, if we had more time, I would press you. Nice. Yeah, you plug in the point that you're given. And so, okay, but where are you going to put the y? Well, remember, if dy dx equals this equation, then the antiderivative is just equal to y. So in other words, we got y equals this. You plug in your points. Let me do that fast before we run out of time. I plug in 0, 1. 1 equals natural log of 0 squared plus 1 plus c, meaning that 1 is equal to natural log of 1 plus c, meaning that 1 is equal to, you guys know the natural log of 1? Oh, nice, okay, yeah. That means what power do I raise e to get 1? And of course that's 0, so 0 plus c equals 1. Therefore c equals 1, and you plug that into here and you're done. Nice. All right, cool. And then just for fun, I'll keep this up if you need it. But just for fun, real quick, let's see how close we were to graphing this correctly. So look at that graph, remember it, and then let's graph this on Desmos and see if it's the same. Did I close this? No, I didn't. And there it is, it's pretty close. There's ours. There's Desmos, pretty close. Cool. All right, good job, you guys. Oh, I gotta stop the video.